my idea is a crazy idea, and I admit it's a crazy idea. But you need something crazy because the conventional ideas don't work. And I think people just sort of go with the crowd. I'm just not persuaded by going with the crowd. It doesn't make sense. I don't believe a word of it. The Big Bang was not the beginning, the same as quantum mechanics. No, there's a huge thing missing.
It's extremely accurate. You could say it's incomplete.
Schrödinger and Einstein were much more polite. They said, well, quantum mechanics is incomplete. It's rather suggests, there's a little detail. Change the sign here. I don't mean that. It's a big thing that's missing.
Standard cosmology says the Big Bang was the beginning. Penrose says that's dead wrong. His conformal cyclic cosmology makes each Big Bang the conformal continuation of a previous eon's remote future. Why? Because mass becomes irrelevant. Twice, in fact, for different reasons. At the Big Bang, there's extreme temperature, and in the remote future, there's only massless photons and scaling of Dirac particles. No mass means no scale, so conformal geometry. This lets the remote future match a stretched-out Big Bang. And this explains why our origin is smooth while black holes are tumultuous. Penrose argues inflation doesn't explain this, but his model does. He further insists that quantum mechanics is wrong, not just incomplete. On this channel, I interview researchers on theories of reality with rigor and depth, and I've been blessed to speak to Roger Penrose 4 times. Once for the Institute for Arts and Ideas, once in a 2-hour podcast last year in Oxford's Math Institute, today for another 2-hour session that you're about to see, and soon again on this channel in a couple weeks with his collaborator, Professor Yvette Fuentes, on a groundbreaking new unannounced experiment. So subscribe for that. Enjoy this episode with Sir Roger Penrose. Professor, what is something that most physicists believe that you think is completely wrong?
Well, there are several things of that nature. I think probably the most blatant one is the cosmology model I have. You see, most people who normal cosmologists these days, believe that the universe began with the Big Bang, and there was an early phase called inflation. And this phase was supposed to have smoothed the universe out. I never believed that. It doesn't make sense. Because why does it work in one direction and not in the other direction? I mean, you get crazy singularities in black holes, which are not automatically smoothed out by time-reversed inflation. It doesn't, it's okay, most cosmologists believe in inflation. I don't believe a word of it. Mm-hmm. But this is just part of the story. You see, the story which I have is that the Big Bang was not the beginning, that the universe goes through cycles. The cycles each one starts with its own Big Bang, terminates with a remote future. You see, this is the thing you have to understand, is that the scheme at both ends, the conformal structure of space-time is the relevant thing. Conformal structure, to get an idea, it's useful to think of these Escher pictures with infinity. See angels and devils, and they crowd out along this circle boundary which represents infinity. And this is a conformal representation. Now, the same thing applies, I claim, to the universe as a whole. And our remote future is a situation, you see, I'm arguing that there are 2 times, if you like. At each of these times, mass becomes irrelevant. One of them is at the Big Bang. Mass becomes irrelevant because the temperature gets so high that the particles move around so fast that the mass contribution becomes trivial. I mean, the main contribution is the kinetic motion, and the actual rest mass of the particles becomes less and less important the closer you get to the Big Bang as you go earlier. So that's a situation in which mass becomes irrelevant at the beginning. And another place where mass becomes irrelevant for a quite different reason is in the very remote future. And then I won't go into the reason in detail. That sort of shifted with from my early arguments. But the massive particles, the mass term scales in such a way that it becomes irrelevant in the remote future. Certainly Dirac particles, and the Dirac particles will be the main particles, apart from photons. Photons are already massless. The other particles mainly will be Dirac particles, electrons, positrons, maybe protons, but maybe they decay. Doesn't matter which, they're still Dirac particles. And they will, if you write them in the right way, you can see that they scale out, and so they become effectively massless in the remote future. And so those two ends, the mass disappears. Now, when you don't have any mass, you don't have any scale. The geometry is really what I call conformal geometry. Well, it's not what I call it. Mm-hmm. It is conformal geometry. And the conformal geometry, it means, well, like those Escher pictures, you preserve angles. The angles are clearly defined and make sense and unaffected by getting close to the edge of the picture, whereas the sizes are changed. So conformal geometry is the geometry of angles, if you like. In space-time, it's the geometry of the light cones. So you have the null cones, I should say. The null cone gives you 9 out of 10 components of the metric. The 10th component really is the scaling of the whole thing, and that is given by the mass. The scaling of the mass comes from the two most famous formulae of 20th century physics. One of them is E equals mc squared, and the other is E equals h nu, hf, if you like, due to Planck. So the Einstein E equals mc squared and the Max Planck E equals hf, or h nu. Put the two together, and that tells you that frequency and mass are equivalent. You see, the energy is one, and energy is the other. So frequency and mass are equivalent. So that mass is what gives you the scale. So it determines a frequency, you see. If you don't have any mass, you don't have the notion of frequency, then you don't have scale. So you have conformal geometry. And the two places you don't have mass, I argue, is in the remote future, because the Dirac particles is all that's left and they scale away, and the Big Bang, where you have energy so great that the mass becomes irrelevant. So for quite different reasons. But then the argument is that then a remote future, from a conformal perspective, is very like a stretched out Big Bang. And the reason for this perspective is that the Big Bang is extraordinarily special in the sense that the gravitational degrees of freedom are not activated for some reason. And this isn't explained by inflation. It's not explained by any conventional cosmology. However, it is explained if you say that the Big Bang is a conformal continuation of the remote future, because you find that the gravitational degrees of freedom scale away. It's a little bit of a subtle question, because gravity has two different scalings. One of them goes away and the other one stays with you and enables gravitational signals to get through from one side to the other. But anyway, that's a scheme which I think there's a lot of evidence for, but people pay very little attention to it. And certainly it's not the majority view is to have a Big Bang and inflation and all that stuff. So that's perhaps the main example where I hold a different view from most people. Another place where I hold a different view, I think, has to do with the collapse of the wave function, which I believe is a very important phenomenon, well, you see, there's no common view on that one, I think, you see. With the cosmology, there is a common view that the Big Bang was the beginning, and for some reason trying to be argued that inflation was the reason, but it doesn't really work, that the uniformity of the Big Bang, which distinguishes it from the incredible complication that you expect for singularities in black holes, Um, they're so utterly different in nature. So you need some explanation for that. The other element has to do with the collapse of the wave function. But there isn't really a common view, I think, that is held by most physicists. I'm not sure what most physicists think. They usually sweep the problem under the carpet, I think, as far as I can make out, without recognizing it's a serious problem.
So two of the other problems that inflation solves, one is flatness that you mentioned, but two of the other ones are the uniformity of the CMB, so the horizon problem.
Well, the fact that you don't have gravitational degrees of freedom. I mean, people don't sort of recognize that very well. I don't know what you see. I found it very puzzling because the expectation inside black holes, of course, we don't know what goes on inside black holes, but the expectation from independent calculations from a Russian group, Belinsky, Lifshitz, and Kalatnikov, and Charlie Misner in Princeton, and they have pictures of the complicated situation that you get as you get close to the singularity, and it's very complicated. You find curvatures go wild and in different directions, and one direction takes over and then another one, and it's very complicated. Nothing like the Big Bang. I don't think people think about the problem, really. It's not that they have a different view from me. They have a different view, but they actually don't face up to the real problem. They have this belief somehow that inflation solves the problem, which is, in my view, completely wrong.
Where does that belief come from?
The fact that you don't have this kind of singularity in the Big Bang. And so the belief has to come from somewhere. And so the inflationary point of view seems to be, that's all they can think of, I suppose. I don't know. I mean, it's very commonly believed inflation is part of standard cosmology.
I was speaking to, it was either Leonard Susskind or Neil deGrasse Tyson, and I was asking one of those two, I believe it was one of those two, what is it that you disagree with your colleagues about? And then he thought and said, if I disagreed strongly with my colleagues about it, then I probably shouldn't be thinking it, because something that they believe in the wisdom of the crowds, they believe that they're the ones that are most likely incorrect if everyone else believes something different. How is it that you can maintain this level of, maybe belief is not the correct word, conviction, credence in your own ideas, despite being criticized by colleagues? How do you psychologically deal with that?
Just that the arguments are wrong. I mean, I don't see any good arguments against my point of view. I mean, the thing about the cosmology is that it's a crazy idea. My idea is a crazy idea, and I admit it's a crazy idea. But you need something crazy because the conventional ideas don't work. And I think people just sort of go with the crowd. I'm just not persuaded by going with the crowd. It doesn't seem to me. I mean, there are lots of things I don't know anything about. And then I say I'll trust the crowd because I haven't got any views of my own. I would say particle physics is a good example. I don't have any particular views of my own, so I'm quite prepared to believe what the most people think about particle physics is probably on the whole correct. I don't know. I don't have an opposing view on that. So,
have you always been like that?
I don't think my own views have been worked out enough to have a strong opposing view to what other people might think. I mean, it goes back, I suppose, to the singularity theorem I proved, which eventually got a Nobel Prize, which was the...
I heard about that.
You see, that was it was at a time when people were very puzzled because of the quasars, and they found these very bright objects, very distant objects, and people weren't even quite sure how far away they were. They weren't sure that the redshift you saw was actually a cosmological redshift, or might it be some gravitational redshift or something like that. There was a lot of puzzlement about it. So it was at a time when there was a lot of confusion, I think, about what was going on. And I became interested in this, but without holding a particular view of my own. And I did learn about the Oppenheimer-Snyder collapse picture of a collapsing cloud of dust. In fact, it was. And this reached a singularity at the end. And this was well known to people, but nobody trusted it for the very good reason that this assumes exact spherical symmetry. So that you might think that if it's not symmetrical, it would get more and more complicated as it collapses, and then it might swirl around and come swishing out again. So I think that was the common view at the time, that although Oppenheimer-Snyder was well known, it didn't seem to represent reality in people's view, which was a reasonable point of view, I think. And I didn't know what the answer was. There had been a paper at the time written by Lifshitz and Kalatnikov, two Russians, and they seemed to have proved that in the general case you would not get singularities. And I looked at the paper. I didn't sort of go into it very hard. I thought the techniques they were using were not likely to be trustworthy. I didn't see the mistake in the paper. There was a serious error in the paper, which was later found by Belinsky, I think, who corrected the mistake and joined the other group. And the later paper came to the opposite conclusion, that singularities were generic, that they did come about like that. But that was not the view at the time. The view at the time was that Lifshitz and Kalatnikov had shown that singularities didn't occur in general, and therefore the Oppenheimer-Snyder collapse, you'd have swirl around and maybe it would come swishing out again. I began to worry about this problem, and I wasn't sure I believed Lifshitz and Kalatnikov. I didn't take them very seriously, probably not for a very good reason. That's mainly I hadn't looked at the paper thoroughly enough. I certainly did not see the error in the paper. That was seen by Belinsky later on, I think. However, I did think about whether this was likely to be correct or not, and came to the view that probably singularities were generic. And I'm not quite sure why I came to that view. I had been thinking about related problems, and I probably vaguely formed that view. But I didn't have an argument for it, and I told this story many times, but Ivor Robinson, who was a very good talker, and he wrote his papers by talking, and somebody else would co-author them with him.
Right.
He would never write them himself. But anyway, he talked very elegantly, and he was talking to me. I was on my way to my job at Birkbeck College, and I remember we were walking along the street, and then there was a side street. We had to cross the road, and as we crossed the road, the conversation stopped. And when we got to the other side of the road, his conversation started again. And then when he left, I was left with a strange feeling of elation. Why do I feel elated? I thought. I can't think. So I began to think all the things that happened to me. What happened for breakfast? No, nothing to do with that. Walk in the woods to get to the bus stop? No, that can't have been it. The bus trip? No, the train, blah, 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 blah. And then I thought, it was when we crossed the road. I had an idea. That was it. And so I reconstructed what that idea was, which I think was, I've never quite got this straight, but I'm pretty sure it was the idea of a trapped surface. You have to have some criterion, which is a generic criterion, so it doesn't assume that you have symmetry or anything like that. It just tells you that the collapse had gone to irreversible place. And this was, you have a surface and you look at the boundary of the future. Well, you look at the future region of that thing, and it has converging lines on it. And I knew enough about some of these things to show that this would lead you to a contradiction. And then there must be something wrong, and that singularities were generic.
I've been using Claude for my research and podcast prep, and is fundamentally different from other AI tools. What makes it stand out is how it thinks with you, rather than just answering questions. Claude was built by Anthropic and founded by Dario Amodei, former VP of research at OpenAI, as a public benefit corporation focused on AI safety. The latest models are Claude Sonnet 4.5, that one's particularly great, by the way, just got released a few weeks ago, and it balances intelligence with speed perfectly, especially great for coding. And then there's, of course, Claude Opus 4.1. These, in my opinion, and by some objective measures, are the world's best coding models. Here's what I use on a daily basis. Firstly, I have the Claude Max plan, and I use Sonnet 4.5 to help build tools for research for this podcast. I build little applets that allow me to interact with it to better prepare for guests. I actually used their artifacts feature live during this podcast with Eva Miranda. And I also used it at the beginning of the Stephen Wolfram podcast to generate cellular automata. For technical work, there's Claude Code, which is a command line tool that lives in your terminal. It edits files, it handles Git operations, it understands your entire code base, it understands my work context, so my previous Python scripts, and it's a joy to use. Of all the CLI agents, this one, Claude Code, is by far the one that I use the most and enjoy the most. Get 50% off Claude Pro, including access to Claude Code, at claude.ai/theories of everything. That's all lowercase. Again, that's claude.ai/theories of everything for 50% off. The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount.
And that singularities were generic. And then I gave a talk about this. The thinking about this, yes, that's right. I gave a talk about this at King's College London. And the movie, according to the movie, Stephen Hawking was there being inspired and sparks coming out of his head or something. Mm-hmm. He wasn't there, but it's not quite so bad as that, because I did give a repeat talk. It was at King's College London I gave this talk. I gave a repeat talk in Cambridge. Dennis Sharma had heard about my talk and asked me to give another talk in Cambridge. So I gave a repeat, and Stephen Hawking was present at that talk. And I talked to him afterwards, and mainly it was the talk afterwards, which I had to him and George Ellis, and I think Brandon Carter, at least for some of this discussion, in which I described the details of the proof that I had. And Stephen then picked up on some of these ideas and generalized them so as to apply to the Big Bang and things like that. And then later on we collaborated on a paper which was very general arguments. Curiously enough, it didn't quite include my original theorem. So the original theorem was not a corollary of what we did in that more general paper. I don't think. No, because we had a different condition on the energy condition was stronger.
We were talking off air about what is it that you're most misunderstood about?
I would think the consciousness thing, probably. The trouble is that's a murky subject, And probably, I'm not sure I should have got into it at all. It's a good question. I think I'm glad I did. But it came about mainly from talks. You see, this was one of the 3 courses I went, which were nothing to do when I was a graduate student in Cambridge, and I went to 3 courses that were nothing to do with my subject. One was by Hermann Bondi on general relativity, one was by Paul Dirac on quantum mechanics, big influence on me, clearly, and the third one was by a man called Steen on mathematical logic. And I learnt about the Gödel theorems, and I found it absolutely stunning, because I had sort of vaguely heard that Gödel's theorem showed that there are things in mathematics you couldn't prove. I didn't like the idea very much, but then when I heard what it actually said, I found this stunning, because what it says, you make a sentence, and this sentence says, it's clever to make it do it, but you make this sentence say, in effect, I am not provable by those rules. And that's what it says. So you say, well, maybe it's false. And if it's false, it is provable by the rules, and therefore it's true and not provable by the rules. Amazing. So how do you make it do that? Well, that's the trick, of course. But what I found remarkable is that how do you know it's true? You know it's true not because of the rules that you're using, but because you believe that those rules only give you truths. And what's the point of using these rules as methods of proof if you don't trust the rules? Why is it proof anyway? Why is it something which you believe to be true? Only because you trust the rules. But if you trust the rules, then you can prove this other statement, which is based on your belief that the rules only give you truths, but you can't obtain that using the rules. In fact, it wouldn't be much good if you did use the rules, because you have to know that the rules only give you truths in order to trust the conclusion. So you have to understand why the rules only give you truths. So then I'm going to think, well, what does understanding mean? I mean, what are you doing? Well, it seems to me, whatever it is, it seems to involve consciousness. I mean, the very term understanding, you wouldn't really say an entity understands something unless it's aware of it. That's normal usage of the language. So to understand something, you have to be aware of it. So for some reason, the awareness of things gives you something beyond what you could achieve with computers. So that is a view which I held then and still hold, which is more relevant than ever now, of course, because people talk about AI, which is already a misnomer as far as I'm concerned. It's not artificial intelligence. It may be artificial cleverness or something, but it doesn't involve any understanding. You're just following the rules. And the argument that I'd convinced myself, learning from Mr. Steen about the mathematical logic, was to say that the understanding of why the rules work is something which is not a computational thing. What is it if it's not computational? Well, it's something to do with consciousness. Now, you see, I don't know anything about what I wrote my book, The Emperor's New Mind, to try and express this point of view. And I learned a bit of neurophysiology, thinking that if I learned enough neurophysiology, I would find out somewhere what it is that maybe... You see, I've formed the view. Yes, I have to backtrack a little bit. I formed the view thinking of all the laws of physics. You see, I'm a physicalist, so I believe whatever is going on in our heads is following the laws of physics. But what are the laws of physics? Well, the laws of physics, Newtonian mechanics does pretty well, but then you have to go further than that. You have to have Maxwell's equations. You have to talk about special relativity, general relativity, and quantum mechanics. But all these things, although there's a little bit of what do I call it? incompleteness in the argument. You see, all these theories depend on the continuum. And there could be a catch there, that something is not based on the continuum. But the continuum seems to be how you can approximate. You can approximate the continuum and calculate very accurately. Even at that time, there weren't good calculations on general relativity, but I realized that was still a computational problem. And nowadays, people do great things with calculators on computing what happens with black holes spiraling into each other and things like that, which is pretty impressive. So sure, that's things you could put on a computer. General relativity, as well as Newtonian mechanics, Maxwell's equations, all these things you can put on a computer. Quantum mechanics, well, the Schrödinger equation, you can put that on a computer. Maybe lots of variables you have to worry about and so on and so forth. But still, it's still the same sort of thing. How about the collapse of the wave function? Well, that seemed to be the gap that maybe is where one needs a gap in this whole discussion. And that's the only gap that I know of. It could be there's something else, of course, that we don't know in physics, but that seems to be an important gap. And collapse of the wave function. You see, many people, including Wigner, I remember talking to Wigner when I was in Princeton. And I remember I had dinner with him and
yes,
discussing this question with him, because one of the views attributed to Wigner was that it's the conscious being observing the quantum system which collapses the wave function. So it requires consciousness to make the collapse work. I talked to him a bit, and he was not so dogmatic as people tend to think about this. He said that was a view that he played with and thought it was a possibility. I didn't think it was at all likely for all sorts of reasons. Seems to me that I had this argument about a distant planet, which is an Earth-like planet, and the weather on that planet, there's no life. It just never got started. And there's no butterfly to flap its wings and cause the weather to do this or that. It's just a quantum mixture of all the different weathers it can possibly have. And there's no conscious observer to look at it, so it's just a quantum superposition of all these different alternatives. So the space probe, which travels out, takes a photograph of all this superposition of all these different weathers, and when it gets back to Earth or close to Earth, it sends a signal to the Earth and says, "This is the photograph I've just taken," and somebody sitting looking at a screen sees this superposition of weathers. First time a conscious being has seen it, whoop, suddenly it becomes one weather. Doesn't make any sense. So that's not what I believe. It's not that consciousness causes the collapse of the wave function. My view is almost the opposite. It's that whatever consciousness is, it depends on the collapse of the wave function. That there is the only thing which I could see which was not obviously computable. Okay, the way we do it is we just introduce a randomness, but that, I would argue, is an approximation, that there is something going on which is not just explained by randomness. But I don't have a solution to that question, but it was my entry into the consciousness discussion. And I wrote my book, The Emperor's New Mind, to try and explain this point of view. I had no answer. I remember getting to the end thinking I would learn about the Hodgkin-Huxley nerve transmissions and I would learn enough about that to see what the answer might be. No, I didn't. So I just sort of tapered off at the end with something I didn't really believe. And that was the end of the book. But later on, I learned from Stuart Hameroff about microtubules, which I thought were much more likely. Something in microtubules could easily be more likely, but the subject is not something. It involves biology. I don't understand about biology. I can't remember the names that people keep using, and they talk about different chemical processes, and it's all beyond me. So
right.
So it's not something that I feel I could develop thinking in. So I did have lots of discussions with people, but the discussions sort of went off in different directions and not anything which I could really contribute to. I think there's interesting aspects about the collapse of the wave function, most of which I didn't know at the time, but thinking about later, there's something extremely puzzling about how it works with regard to time. And this puzzlement could easily have relevance to conscious perception and things like this. So I think there's a story there which is worth exploring, but it's not really an area which I can never remember the names that people talk of, the chemicals which are involved and so on. And it's not the kind of thing I can do. So I'm happy for other people to follow these lines up, except that I don't think they've got very close as yet. I don't know. It's quite possible that this is not my idea because I can't really contribute. But one thing I would worry about is you have the cerebrum and the cerebellum underneath. The cerebellum is organized much more in the way that if you're a computer scientist, you would organize it. The left-hand part controls the left hand, the left side of the body. The right-hand part to do with the right-hand side of the body. There's none of this crazy crossing over and all that stuff that the cerebrum is involved with. It's much more organized like a computer. It's completely unconscious. It is like a computer, maybe. But the thing that impressed me a little bit about what Stuart Hameroff was doing later on is that he considers that this main relevant structures in the brain have to do with things called pyramidal cells. And that's the first time I've heard about certain types of cell which are not found in the cerebellum. Everything else you see is the same kinds of cells and so on and so what. But these cells occupy a particular location in the brain, and Stuart seems to think that they are very important with regard to consciousness. I can't make any comment there because it's not my area. But I do find that particular suggestion as quite plausible. That's all I can say.
Now, if you're a physicalist and you believe that the collapse of the wave function somehow produces consciousness, then I don't see that as inconsistent with a computer being conscious, because a computer is a physical system after all.
Well, no, it would have to be harnessed, and you would have to make use of it in some way. You see, it's physical in the sense that the collapse of the wave function is part of physics. It's not to do with an observer looking at it, as I was saying earlier. It has to do with the system getting too big in some sense. And that's another line of thinking which I've developed to some extent independently. I had an argument which I put forward around about the turn of the century. I can't remember exactly when. And it came up, this argument produced a lifetime for a superposition. So if you have a body, take this cup, forget about the coffee in it, take this cup and imagine it's in superposition of being here and here. Well, I can tell you that will have a lifetime of becoming one or the other. What is that lifetime? Well, I work out if I take two copies of the cup right on top of each other, I move one of them away from the other. I ask how much energy that would cost me if I consider only gravity. So the gravitational force between the particles as I move this away is tiny, but still huge in another respect. That energy is a fundamental uncertainty whose reciprocal gives you the lifetime. So the lifetime for this cup would be absolutely instantaneous. If it's a molecule, maybe not. Maybe it take a long time. If it's a big enough molecule, maybe the collapse would happen quite quickly. Depends how big it is. But that calculation tells you the lifetime. I should say that lifetime was independently discovered independently about 2 years before me by Diyoshi. So that you can call it the Diyoshi lifetime. I sometimes call it that. However, his scheme is in a way different from mine. And he still had an argument for a lifetime, but it has other implications in his scheme which have been refuted. There was an experiment done a few years ago, about 3 or 4 years ago, I can't remember now, in a mountain, because his point of view would predict that the collapsing is happening all the time, and this gives you an effective heating. And so the system would gradually heat up. There would be a slight spontaneous heating, and that heating is measured not to take place. So some people say this disproves the Penrose theory, but it's not the Penrose theory, because my scheme does not involve the heating. It would be a nuisance, because I think it would cause real problems with cosmology. You have neutron stars would already be heating up spontaneously in a way that they don't. So I don't believe that. But in order to avoid the heating problem, you have to have something else, which is very curious. And this curious thing depends on certain things being retrocausal, as though the cause goes back into the past. But you can only make sense of this if you have what I call 2 kinds of reality. One is classical reality, and the other is quantum reality. And classical reality, well, the cup here has classical reality. I can say, hello, cup, what's your shape? And it can say, well, I've got more or less a circle up there, and I have this particular curve there, and it's actually symmetric apart from the handle, and so on. You see, that's classical reality. I can ask it what its shape is. Quantum reality is better described by, say, the spin of an electron. The spin of an electron, the spin state could be in any direction in space. But it's the quantum superposition of only 2 directions. If you want to ask it, you say, See, Einstein had a criterion. See, I think people were worrying about whether the quantum state was real or not. When I say real, I don't mean real in the mathematical sense, as opposed to complex, because it's complex numbers.
Right.
But I mean real. Is it physically real? And Einstein had the following criterion. He says, if you have a state that you can perform a measurement on the state such that it gives you the answer, yes, you've got the right answer, yes, with certainty, that gives it a reality without disturbing the system. That's right. If you can make a measurement without disturbing the system to say, are you like a spin half particle, say, is your spin in that direction? And if you got it right, it will say yes with certainty. That's Einstein's criterion for the reality. I'm slightly changing the terminology. That is, in my mind, the criterion for quantum reality. You can't say, hello, particle, which way are you spinning? Or you can say that, but it won't tell you. It looks at you blankly and says, I don't answer questions like that. Suggests a direction, you see. Then you can suggest a direction. If you got it right, it will say, yes, you got it right. If you've got it wrong, it may say yes, it may say no, with various probabilities, depending on where. If you've got it completely wrong, opposite right, it will say no with certainty. So Einstein's criterion is satisfied, but you can't ask the particle which way it's spinning. That's quantum reality. So you have to distinguish between the quantum and classical realities. And the quantum reality has very curious causal behavior. It looks as though it goes into the past and things like that. So you have to be very careful about it, that it doesn't give you a causal anomaly. Somehow you could predict the past or something, retrodict. So it doesn't do that because it's only quantum reality. But it's a curious kind of situation, which I have written about, but not probably sufficiently detailed. And I'm thinking about writing a paper which would explain this more completely. It's actually in my book, Fashion, Faith, and Fantasy. So it's in the book, but perhaps it needs a little bit more
sharpening up.
Yeah.
Do you see this quantum and classical reality as completely distinct? Because most of the time, people think of the classical world as the limit of large n or large amounts of quantum systems.
I mean, you can have a quantum system which has a huge spin, and that spin is still quantum reality. It's not going to give you a classical answer just because the spin is large. So the fact that your state involves many degrees of freedom, what do you mean by large, you see? Does it mean lots of degrees of freedom are included? In which case, I don't think that's the answer. The answer has to do more with mass displacement. And then, yeah, it depends on them moving the glass and so on. So the classical reality, it's not a fully worked out scheme. I don't know the answer to most of these questions. But all I would say is that I think this criterion for collapse for a body in two locations is a fairly clear-cut formula. I said the Dioschi time scale for collapse. But it's not just because the system is big in the sense of having many degrees of freedom. Depends what one means by big, I suppose. Big in the sense of mass displacement, yes. That probably is true. But then you see let me put it like this. It depends on combining with general relativity. Now, often people say, what is the major problem of physics that we don't know about? And they say quantized quantum gravity.
Mm-hmm.
Now, I say that's the wrong way around. Sure, that may be a big problem, and maybe someday, well, some people have some answer to it, but what good will it do you? It might tell you what happens inside a black hole. That doesn't do you much good anyway, because black holes you see the outside of them, you don't see what's going on inside. If quantum gravity is playing its role right in the middle, as maybe it does, it doesn't help you very much. However, the other way around is a huge problem. Well, a huge issue to be resolved. And what I say is the gravitization of quantum mechanics. And the collapse of the wave function is what I'm really talking about. Because you see, I'm saying the collapse of the wave function is a gravitational effect. It depends on bringing ideas from general relativity. See, to be more specific, the criterion that I come to here comes from the principle of equivalence. Principle of equivalence, which says that gravitational field is equivalent to an acceleration locally. It goes back to Galileo. Galileo is very clear on that point. If you drop a big rock and a little rock from the Leaning Tower of Pisa, I mean, I'm not sure he ever did that, but the theoretical discussion, if you got rid of the atmosphere, sure, if you drop a feather, it hovers away, but then that's air resistance. He knew all about that. So it was, sure, if you could get rid of the air, a big rock and the feather, as people have done now on the moon or something, it was showing that Galileo was right by dropping a feather and a rock on the moon. Quite a nice demonstration. Mm-hmm. Of course, you can't expect anything else. But what it means is that locally, you can get rid of the gravitational field. But now you combine that with quantum mechanics, and it's not quite so simple. And you find that you have to monkey about with the wave function in a way which looks as though it's just a little technicality. But when you think about it in a more broad context, you see it's not just a technicality. It tells you there's something funny going on when you try to combine the basic principle behind general relativity with quantum mechanics. And it tells you, in my view, that you have to have collapse of the wave function. And that collapse timescale is the same as Dioschi. Tells you the mass displacement. You do that calculation, which I did. Tried to move the cup away from itself, how much energy is that in terms of gravity alone? And that energy gives you a lifetime. And that lifetime is physically there. But for this cup, it would be instantaneous. It behaves classically.
Have you played around with modern LLMs? Like ChatGPT or Claude?
The only thing I ever did was there was some primitive version of this, some mechanical woman. What was her name? I can't remember. She was a robot.
Oh.
And I did talk to her, and I thought she was incredibly stupid.
Oh, okay.
I mean, you have to keep to the subject. I think I said behind you there was a cat or something, which is not looking very happy or something. I don't know. I remember.
Sure.
She hadn't the foggiest idea what I was talking about. There were only just a certain number of sentences it could respond to. And I thought it was very stupid because it said at one point that this mechanical woman, somebody had come and talked to her, and the mechanical woman said, "We're going to try something different now. We'll try meditating." So they sat there not saying anything at all. Neither the person nor the robot was saying anything at all. I thought, this is a big cheat. Oh, dear. I'm sure it's a lot better than that now. Much more convincing.
Well, the reason I ask is that with the modern LLMs, like Gemini or Claude or ChatGPT, you can ask it to explain Gödel's incompleteness theorem to you, the first one, or the second one, but let's just say the first one. And then it will, and then you could ask it to prove it, and it will, and you could even show it your own version of the proof with some small subtle error, and it will say that's an incorrect proof. Why? Because of this and that, and it will get it correct. So does that at all chip away at...
No, I don't think so. I don't find that all that impressive. I suppose whether you can talk. I mean, people call it the Turing test, and they say it's past the Turing test. But then that really depends on who's doing the Turing testing. You have to have somebody who really knows what they're talking about. Just an ordinary person talking without just talking ordinary about what happened to them when they came to work in the morning or something. I don't know. I've not been involved with these things recently. I find it scary in the sense that really because people believe it's conscious and probably it will do things. But then there are examples that I suppose this is a well-known example, but Helen was telling me this example. What was it? I have to think of the right word. It's a word with raspberry, I think it was. Raspberry.
Oh, right. Yes.
How many R's are there in raspberry?
Strawberry.
Strawberry, was it? Strawberry. How many R's in strawberry? And it said 2. And then the person would say, well, let's count them out. And you say, there's an STR, there's one. And then double R there. How many R's in strawberry? 2. Didn't we say just 3 of them? It's 2. That's not intelligence. It's taking a sort of average of goodness knows what. Data, conversations, and somehow averaging it out. I don't know. I find it worrying because it's clearly not intelligent. But it could be sort of persuasive enough to people that they think it is. I guess there are even people who have girlfriends and boyfriends, which are simply AI systems, which is a bit worrying, I'm afraid. I don't know. I've never had not like this crazy electronic woman, which I talked to before, which was incredibly stupid. I'm sure they're a lot better than that. And they can probably fool you for a while. Most conversations, you speak to somebody and they're fairly automatic. They don't really involve the person you're speaking to being aware at all. But so you could probably fool people quite not too hard. I don't think probably you could fool somebody who's an expert on testing these things.
What is intelligence to you?
I don't know. All I know is that whatever it is, it does involve awareness. So I would say that whatever intelligence is,
It's a mental state somehow.
well, it doesn't, there's something going on, sure, which has to do with consciousness. And don't ask me what it is, because I don't know. All I'm saying is that I don't think it's a consequence of the laws of physics that we currently know. But then the main laws that we don't know have to do with how the gravitization of... say it's the other way around. People say quantum gravity is the big mystery. Well, maybe it's a good mystery, but that's not the main mystery. The main mystery is the gravitization of quantum mechanics. See, quantum mechanics has a huge hole in it. It's the collapse of the wave function. And lots of people hold all sorts of different views about that, or they don't think about it. They say, well, you shouldn't stop thinking about that. But it doesn't make the answer there. There's an answer. The wave function spontaneously collapses. And it doesn't seem to be whether a conscious being is there or not. That's something else. So my argument is that it's not the conscious being which collapses the wave function. It's the collapse of the wave function which creates the consciousness. But how it does it is a very, very subtle, far off. We're not close. I don't think we're close.
Would that mean that black holes are conscious?
No. Don't see why. Just because they're big? No. Don't see why they're conscious. There's no collapse of the wave function involved in the black hole, as far as I know. I mean, maybe to make one, you've got to do a bit of that on the wig. But a black hole is a very classical object. Depends on general relativity. I see no reason to regard that as being conscious, no. I could be wrong.
Do you see the black hole information paradox as a problem?
No, I don't see it's a paradox either. No, it's stupid. Oh, dear. You see, people say they don't like information to be destroyed. That's why. And black holes seem to swallow information, and so they like to think it comes back again with Hawking evaporation. I have no reasons to see why it should come back again. I don't see why it shouldn't be destroyed. As far as I can see, it probably is destroyed in singularities. It's putting something we believe about classical physics onto, I don't know. I don't see why it needs to be. I don't regard it as a paradox. You see, there's sort of two strands to this. You see, people say, oh, well, it's a paradox, and you resolve the paradox by Hawking evaporation. And this means that the information comes back again when the black hole evaporates. I don't think so. It's completely different information which comes out. It's not even information. The word information, unfortunately, I think carries too many. It carries a certain implication that there's something, it means something, I guess.
Right.
I mean, it doesn't mean it. I mean, the evaporation of a black hole doesn't mean anything. It's just temperature, as far as I can make out.
Is this something that you disagreed with Hawking about?
Probably, yes. But I did disagree with him a few things, yes. I can't remember. I remember the last conversation I had with him, he didn't even talk. He was very ill. I mean, he gave a talk, actually, he gave the first of these so-called Penrose lectures that we have here in Oxford. And it was a good talk, actually. I thought he was not bad at all. And he did refer to the gravitational horizon size, in the black hole horizon increase. which he hadn't given me any credit for previously, but he did in this talk. Now that was a rather disturbing. I can see how it came about. You see, I had a conversation with Stephen where I described to him the black hole area increase, classical phenomenon. And I stayed the night in Cambridge. This was a talk I had in some lecture room. I described this idea to him. And then in the morning, he phoned me up while I was still in bed, I think. And he phoned me up and he said that this idea, he had a new way of looking at it. If you could say a pair of black holes, if they collide, then you can get an inequality on how big they are and so on from the area. And the area, combined area of the two holes, and the final area gives you a limit on some inequality. And I said, oh, that's a wonderful idea. I hadn't thought of that. How do you know where the horizon is when they're separated? He said, oh, well, they've got to be close, very close to them. And I said, oh, yes, I see. And then he wrote about this, you see, without giving me any credit, which did irk me a little bit. It really should have been a joint paper, which he did admit afterwards that the idea came from me. But I hadn't thought of using it in that way. So it was certainly that was him.
Yes.
But the earlier part of seeing the area business was something I told him, which he sort of grabbed himself. And then but in the talk he gave in Oxford, he was more generous, and he did explain the idea came from me. It was curious. So no, it was really different. It was awkward with him in many ways. Because of course he did have terrible problem. I mean, what do you do? And I sometimes travel with him to a conference in Europe, and I'd come back with him on the plane. And I remember one occasion when somebody who was driving us to the airport took a wrong turning. Oh dear, that was terrible. And he finally got us to the airport almost much too late. And I remember racing, pushing him down up one ramp and up another one, finally getting to the plane, and the door was about to close.
Wow.
Finally, I think they were waiting. They knew that we were coming, and they waited enough time for us to get there. But that was a narrow squeak.
You said it was awkward with him at the end?
Yes. I would say so. Well, it was difficult to talk to him. Well, for good reason. No, it's very hard to talk to him. And he would tend to lay down the law a bit about what was... I did try and talk to him about my cosmology at one point. And I'm not sure he understood it properly. Because he'd asked me some question about it, which may have been my fault. I didn't explain it very well. I don't know. But he had a different idea, you see, the Hartle-Hawking view, which I didn't believe at all.
And still don't believe. Why?
It gives the wrong... I'd have to think what it is, first of all. It's something about the closing off the Big Bang with making it... You go into you have to do a signature change, so you're making it positive definite. I mean, I never liked signature changes anyway. It seemed to me the whole idea was wrong. But the idea was if you're doing quantum gravity, you can do that kind of stuff. But I didn't think I couldn't trust anything that anybody did in quantum gravity. I don't think it explained why the Big Bang was so special. I don't think it gave a proper explanation.
Did you ever disagree with Wheeler on the nature of information?
I don't remember talking to him about it, but I probably did disagree with him. I don't remember. Yes, he did talk about information being the most important thing or something, yeah. I never took it seriously. See, I'm not quite sure what information is when people talk about it. It didn't make sense to me. There was, my relation with Wheeler was a bit peculiar in many ways.
Okay, let's hear it.
Well, it was Dennis's idea. You see, Dennis said, you must go to America. He thought that I needed to understand what was going on in quantum gravity, I guess, and things like that. And I got a NATO fellowship for 2 years, which was to go to Princeton. And that was it, in the advice of Dennis Sharma. So I put in for it and managed to I got it. And so I went to Princeton. It was meant to be for 2 years. I stayed about 1.5 years at Princeton. Then I went to Syracuse because a lot of good people were going to Syracuse. And that was useful. More useful in a way than Princeton, I think. Princeton was a bit sort of narrow in its viewpoint, I guess. Well, it was very Wheeler-driven. Wheeler had some very definite ideas about how to do quantum gravity and things like that. And I didn't think they were going to get you anywhere. I didn't think doing quantum gravity is going to get you anywhere. It's really... I don't think I held this view at that time, but it's the other way around, how the gravity affects quantum mechanics. But that was not... I wasn't plugging that at the time. That came much later, I think. Yes, I don't remember much about that.
You mentioned Wigner.
Yes.
You mentioned that he wasn't as staunch about his own interpretation that people at least ascribed to him.
Yes, I think that's true, yes.
So
he was more reasonable.
What did he believe then?
I think he just said he didn't know. But he did think that was one possibility. It was the collapse of the wave function came about through... he was worrying about the problem, which I must say, a lot of people didn't. But he had a genuine view. One possibility was that it was the conscious being looking at the system, reducing its state. I remember having a lunch with him, which I had discussed these things with him quite a bit. But I found him not so dogmatic about that particular perspective as one might have thought. I think he just thought it was a possibility, which he quite liked, I think.
You mentioned you have an Edinburgh story about Ed Witten.
Oh, yes. Yes, there was a conference in Edinburgh. And Edinburgh, as you may know, is divided into two. There's it looks as though there used to be a river, but it's dried up now. I don't know if there's a trickle in the middle or not. But the one side was where the hotel was, where we were staying, and the other side was where the conference was. And so you had to go along this narrow bridge to go to the other side. And I was not very early, and a bit late getting up in the morning to go to this talk.
Mm-hmm.
And whenever I would get up, I would see Ed Witten waiting for me. He wanted to talk to me. So we did walk, and he asked me this question, which was worrying him. He was worrying that the cosmological constant should be negative, because his picture of string, all that stuff required, as far as I know, they still do, I'm not sure, a negative cosmological constant. And I said, no, the evidence is strong. This is positive. You're not going to get away with it being negative. And he was very upset because he wanted me to give him the freedom to have a negative cosmological constant.
He wanted you to give him the freedom.
I think he wanted me to be more open-minded about it. I was just taking the evidence for it. But I don't, it's not much of a story, that one. It's just that he was waiting, didn't mind being a little late for the lecture if he could try and persuade me to have a negative cosmological constant. which I wasn't prepared to do. Just thought the evidence was pretty strong. I mean, there's an earlier part to that story, which is not Witten. The earlier part of the story was to do with an American cosmologist, an interesting fellow. I've forgotten his. Oh, I should know who he is. Sorry, but he was visiting England, and I think we were going into dinner at one of the college, maybe my college. And as we were going in, it was in the early days when the redshift, which suggested that there was a positive cosmological constant, come along. And I didn't like it, you see. At that time, I thought it should be zero. From some idea to do with twistor theory. And I wanted to I had a solution to what I called the googly problem. And the solution depended on it being null, infinity being null. So I have zero cosmological constant. And that was my idea. And I remember going into dinner, and I said, surely this redshift for these dust could be dust, as some people were saying. And he said, no, that doesn't work. It's not just that. It fits so well with all sorts of things, and they've come together so well if you have a positive cosmological constant. So I changed my mind. I said, okay, I'll have to get used to the idea. I'm glad I did, because the whole idea of CCC depends on the cosmological constant being positive. Absolutely, you've got to have a space-like infinity. I knew it meant space-like infinity. I mean, that's work I'd done previously. I knew it meant that, but I didn't want it previously. I tend to visit him sometimes in Princeton. So I went to visit him at one point and had some ideas about twistor theory I wanted to talk to him about or something. I can't remember.
Him being Ed Witten?
Ed Witten, yes. No, I wanted to talk to him. It was useful to talk to him. He had interesting ideas. And so I started talking. He talked to me. He said he started to describe something. Blah, 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 blah. And I said, that looks like twistor theory. And he said, yes, it is. He was using twistor theory to try and do calculations in quantum gravity or something. And so at the end of that, I said, that sounds very interesting. Now, he said to me, I'm thinking of writing a very short paper a short note paper on this. Would be prepared to look at it? So I said, yes, sure. I waited 2 months, and then this 100-page paper came. And that 100-page paper, it was 99 pages, I think, but and I gave it to some of my colleagues and students. And then they went discussing this paper, which was bringing twistor theory in connection with gravitational calculations. And it sort of started off a whole line of thinking in my group. And then we had Ed Witten, we invited him over, and I think he had a combined discussion with all these ideas. I'm not sure it was a good idea, actually, the whole thing, because people got carried off in a particular direction. I mean, it was probably close to when I retired anyway, so it didn't matter too much to what went on, although I kept up my contact with these people. I think I had a view that it probably was carrying people not quite in. It was an interesting to see how the string ideas that he was having did relate to twistor ideas. But on the other hand, later on, I think I thought it was not a good idea.
Why not? And also, do you mind explaining the idea? The semblance that you recall?
I'm not sure I can remember it, though. It was trying to bring, I think, string theory ideas into connection with twistor theory ideas. And it was a kind of set people thinking off and along new directions, which was interesting. Sure. But the thing is, I'm not so convinced about string theory myself. I think I can't remember the details of it because I think I was not really in full You see, it's a time when I'd retired, I think, and so I was not really, didn't have a group of people who were doing research with me. And they went off on their own and developed certain ideas. I probably shouldn't comment too much because I don't think I understand it well enough.
What about Richard Feynman? I know you've told several Feynman stories.
Oh, I've got several of them, yeah. No, there are about 6 Feynman stories, so I'm not sure.
Is there one that you haven't told much? Or at all, even?
I have to think. There probably is one, yes. I don't know, because I usually tell them all, don't I? Tommy Gould's one. See, I first met Feynman at a conference which was being held in Poland, a bit north of Warsaw. And it was just at a time when the sort of Cold War was starting to thaw a little bit. And they had people from both sides of the Iron Curtain, as it then was. And so there were some Russians there too. And Poland already was on the other side of the Iron Curtain. So I remember the thing is that my then wife was very keen on getting a Volkswagen, which we bought we picked it up in Wolfsburg, where they made the cars.
Yes.
And we picked it up fresh from the place where they make them. I think we must have left our old one with them. I can't remember the story exactly. I think that was right. It was a new car. And so I remember driving through Checkpoint Charlie and all that sort of thing. It was all behind the Iron Curtain, you see, at that time. But there was a bit of a thaw. And at this conference, Feynman was there. And I actually talked to him a little bit about some ideas I had about doing zigzag, sort of integrals using zigzags for working out the electron field or something. And he seemed to be quite interested in what I was saying. But I don't know how much of an impression that made. But what I do know is that at the end of the conference, there was a group of people were going to a hotel in northern Poland, where the mountainous area apparently, and it was a question of enjoying the mountain scenery and going to this hotel. But this involved a bus trip to the hotel, and you had to get a complete ticket with the bus and the hotel and then the bus coming back. And since I had a car, I didn't want the bus. So I wanted to go to the hotel. And so we tried to find out where the hotel was, and the people refused. They wouldn't tell us. Nope, we don't tell you. And I complained to Feynman about this. They're not going to tell us about it. So he said, I'll find out for you. So anyway, so the day came, we were just about to drive off somewhere. Didn't quite know where at this point. Feynman came up to us and handed a little piece of paper. Opened a little piece of paper, name of the hotel. I don't know how he'd found out, because they were absolutely adamant not to tell us. And the reason they weren't telling, it wasn't anything to do with the Iron Curtain and all that. Well, it was in a sense. But the reason was they were charging everybody twice as much as the official price.
Ah.
And so we got the ordinary price when we went up there. But people who paid for the tour, they would paid twice as much. And that was the reason. And then we drove back, and I think we did to come back through the Iron Curtain or whatever it was called. But that was my first encounter with Feynman, which wasn't much of a story, really. I think the main there was a beautiful set of photographs people took of this conference, and one of the most magnificent of these is Feynman. Picture Feynman and Dirac. And there's Feynman sort of with his hands like this somehow, trying to explain something.
Yes.
And there's Dirac sort of leaning back, rather kind of
reserved.
Yes.
Yes.
And it's a wonderful picture.
Yes, it captures their personalities.
Captures them, absolutely, yes, that's right. Yeah.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.
Have you ever met Schrödinger?
I very much regretted never meeting Schrödinger, because I used to go quite frequently to the place where Schrödinger went in Ireland. You see, he had an appointment in Ireland at the Institute for Advanced Studies. And I quite frequently went there, but only, unfortunately, after Schrödinger left. The closest I got to Schrödinger was his daughter. One of his daughters, I think, I had a conversation with her, and I met her. And I had two copies of Schrödinger's book, What is Life, or something.
Mm-hmm.
And so she had two copies, and so she exchanged copies. My copy with his signature on it or something. I can't remember. Yeah. No, I never actually met Schrödinger. The one with my signature and hers. I had Schrödinger's daughter's signature. So I met his daughter. But that was a regret of mine, because I sort of could have met Schrödinger. I would like to have met him very much, because I thought he was a fascinating character. And he wrote, I was a great fan of his writings, because Schrödinger was somebody who wrote popular books, or semi-popular, you might say.
Yes.
And very good ones. And I think I had all his books.
Did that inspire you to write your own books?
I think it did. Probably, yes. I think it was an influence, yes. Sort of think if Schrödinger can do it, well, maybe I can. I don't know. Yeah.
Tell me about the writing of Emperor's New Mind. Did you already have those ideas worked out prior to you starting the book?
Well, I knew why I wanted to write it, but what I didn't know was how the brain could be making use of what I think it needed, you see. And so I learned a bit about neurophysiology, and there is a whole section in the book about neurophysiology, and I thought it a fascinating subject. But I learned about the Hodgkin-Huxley nerve transmission, and I said, there's no hope. You can't preserve coherence that way. Doesn't answer my problems. So when I got to the end of my book, I hoped that I would have an answer to see where in the brain there could be something which could employ the collapse of the wave function. And I didn't. It was left blank to me. I couldn't see anywhere. So I ended up with something very weak that I didn't believe in, really. Something about crystals or something, I remember, which is in the book, which my excuse for leading it off. But it was not, no, it kind of petered out at the end. Although there was this description of the experiments due to Benjamin Libet, which I found fascinating. And I think they're not legal to do now, because they should be repeated. There were experiments which had to do with the timing of conscious experience.
The readiness potential and free will, telling someone to decide when to make a movement?
I think they're two different things, you see. Yes, that may have been part of it. It wasn't so much that, it was the sensory aspect. You see, there was a patient who had an operation on the brain for some other reason, and permission was given for Libet, I guess, to perform experiments on this person, which probably would not be legal. So people tell me, which is a shame, because they're fascinating experiments. I do describe them roughly in my book, The Emperor's New Mind, at the end. And the thing is that there's an electrode which touches the finger, and the sensation of that And then there's another electrode in that part of the brain which has to do with the sensation of the finger being touched, sensory part of the brain. And it's all to do with the timing. And there's a clock, which is a fast-moving clock, and the patient has to try and say when he or she feels this. And if you touch the finger, then it's almost instantaneous, apparently. If you touch the part of the brain to do with the sensory that, it takes a little while, in the sense of half a second. Not quite a long time before that part gets, maybe it was a quarter of a second. I can't, I think it's half a second. Not quite a long time in a sense. And then there are things about if you touch the finger first and then the brain sensation. Yes, the finger one seems to be instantaneous. The one on the brain takes half a second before it's felt, before the patient registers feeling it, which is curious, already curious. But if you touch the finger and then a quarter of a second later do the brain stimulation, then the brain stimulation is felt, but the finger stimulation is unfelt. How can you unfeel something which you should already have felt?
Mm-hmm.
So there's something strange about the temporal, exactly when things are felt and so on, which is quite, and this ties in with other things too.
Yes.
Which it seems, for example, if you're playing a sport or something, which I used to play ping pong a lot, not to a huge skill, but I played it, and I would see I think even now the current view is that it takes a while for consciousness, maybe half a second. Now, I think that's ridiculous, because if I want to decide whether to hit the ball that way or that way, I see where I think the opponent is and maybe do it that way, you see. That's much less than half a second. Then they say, oh, no, it's all unconscious. I said, no, I was deciding to do this.
Right.
He said, no, it can't be. It must be. It's an illusion. You're not really conscious doing it. So I don't know if it's the current view now or not, but it had been. The current view is, no, all these things you think you're doing consciously are really unconscious. And I thought, that's ridiculous. I mean, like if you're piano playing, you see, they might touch a note. I mean, piece may be very, lots and lots and lots of notes going within a half a second. And to decide whether to hit this note maybe slightly more delicately than before, that's a conscious decision. No, it isn't. You can't have time to do that. It must be unconscious. But you see, it's probably the timing of these things is not a straightforward issue. When you think something, I don't know. But you see, if it's to do, I can't make any definite statement. All I think is that there's some monkey business going on.
Okay.
When I say monkey business, it's some subtlety which you can't explain using classical physics.
Somehow I knew you were going to say monkey business.
I see.
It's either that or poppycock. But I didn't think that one applied in this case.
Yeah, so it's when monkey business, it tends to me there's something going on there. It's not just random.
I just spoke to a neuroscientist named Aaron Schurger, who's reinterpreted the Libet experiments. And he said that we've been making a mistake seeing that there's this potential that comes on approximately half a second to 1 second prior to us deciding to make some action. You can't go from that to infer that, okay, the decision must have been unconscious, therefore we didn't actually decide it. Because he was saying, well, there's a correlation, but the correlation doesn't imply causation. And then in his model, he gives an analogy. He says, if I put on some measuring devices on you that measure your health across the season, they will show a small dip prior to you getting the flu. Does that mean that that small dip caused you to get the flu? Well, some other people get a lower dip as well, but then don't get the flu.
So there's
Well,
this line of reasoning that he goes through and says that he can get this reaction time for consciousness down to actual reaction time, which is 50 milliseconds or so, which is much more in alignment to you consciously deciding to swing the ping pong ball, rather than what people told you before, which is, no, you think you decided it, but you just unconsciously decided it, and then some post hoc rationalization told you, I decided it. His view is slightly complicated.
Well, I'd be interested to see what it is.
Yeah.
See, my view is it's probably not explicable by classical physics. That there is something, you see, there is something retro causal, nothing to do with this at all. So I usually don't bring this sort of thing into my arguments at all. It's not necessary.
Too speculative?
It's bringing in consciousness, which I prefer not to in this issue. You see, I think that's a whole story, which I've dabbled in, it's true. But it's not something which I could probably seriously contribute to, because it requires understanding too much biology and things like that, which Zach, I sometimes say, listen, sorry, I shouldn't be confusing all my stories. But originally I was supposed to be a doctor. Both my parents were medical, and they had decided that I was the one who was going to. That was before my sister grew up and actually did become a doctor and married one, so they got two for the price of one. But they were very disappointed when I went and did mathematics instead. But that's all sort of irrelevant to the story, except that it's just as well I didn't do that, because I would never have understood. I would never have remembered the different medications that people were supposed to have. I'd have got them confused because I wouldn't remember the different names. That's all I'm trying to say, because when it comes to things like biology, it's really not my area, because it involves different kinds of chemical compounds and what on earth they're doing and which kinds is which and what name is attached to which one. And no, I can't do that kind of thing. So I don't want to. What I'm trying to say is that the consciousness issue, if you're really going to get into what is involved in say, human consciousness, there's a lot of biology involved in that, and there has to be, because that's what we are biological systems. So it's not going to. It's not my area.
I was speaking to Dr. Michael Levin, who's a biologist, a developmental biologist.
Oh, yeah.
He wanted to know, well, what he's doing is extending Platonic space to include biological systems and minds as well. He had a question for you. He wanted to know if you thought Platonic space has its own dynamics, or if it's just eternal and static. So that was one question. And then
I can do that one. It's eternal and static. I mean, there's no temporal, time doesn't come into it. It's just mathematics. And mathematical truth isn't a temporal thing. It's true. It doesn't involve time. Nothing to do with it. I mean, you can talk about physics, and of course that involves time.
His second question was, do you think this Platonic space includes more than just mathematics?
Well, I'm using it depends what you mean by Platonic space, I suppose. I'm not sure I understand the question. You see, the Platonism I refer to in the sense of mathematics having its existence independent of us, independent of mathematicians. It's to do mathematics is a bit more like archaeology than you might think. There's the Platonic world out there, and you're digging away at it, and you find some beautiful result, which is sitting there waiting to be discovered, or it doesn't care whether you discover it or not. That's not its concern. So the mathematical world is there. It's not created by us trying to do mathematics. That's the only sense. But when you say giving something else a Platonic existence, that sort of, I don't know quite what that means. Were you trying to, what was the thing?
Okay, let me read the question for the audience as well.
All right.
You've said you're a Platonist about mathematics. Does the mathematical realm exist independently of physical reality? Is the Mandelbrot set out there even if the universe didn't exist? And do the contents of Platonic space have dynamics of their own? You've answered that already. What's the best way to think about the interaction between Platonic objects, which presumably don't have time, and physical objects, or processes, which operate in time?
Well, I've usually, I have this sort of triangular picture, which I like to draw as an impossible object. And these are what I call the three worlds and the three mysteries. I mean, I used to talk about this. I haven't done it much recently. And the worlds are the Platonic mathematical world, and the physical world, and the mental world. Yes, and then they see but then the connections are the three mysteries. So I'm calling them mysteries, you see. One of the mysteries is the physical world and how that depends on mathematics, which seems to be a very close connection. But not everything in the mathematics. The way I draw it is only a little bit of the mathematical world seems to be governing. See, there is a sort of view that people have, oh, this is such a beautiful piece of mathematics, it must have a relevance to the physical world. Not at all. There's no reason why it should. So there's a lot of very beautiful mathematics going on, which, as far as we can see, has no connection with physics at all. Of course, it might have some distant physical theory that comes about, but I don't see any reason why it should have. This comes out particularly with things when they talk about higher dimensional theories, you see, like in string theory and all that. They like to use these different dimensions of space and so on. I don't see any reason for that at all, just because you've got a mathematical theory which can exist in higher dimensions. No reason why physics should follow it. And then you see, again, there's a next mystery, which is that only part of the physical world seems to have consciousness. So that's a mystery too. And then I say, well, most of conscious activity is not thinking about mathematics. Even if you're a mathematician, you like to have your lunch too, and you like to
have your cappuccino.
Exactly. So it's not just mathematics. And I don't know how much most mathematicians think about mathematics, but certainly it's not all the time with me. A little bit, only a small amount of the time, especially when I get older. I can't, it's harder for me to think about it.
I know you called yourself a physicalist, which is a monist, which means there's only one kind of substance and it's just a physical substance. The way that I read your work is at least a dualist. It could be a trialist because of this. So there's the physical realm, the mental realm, and then the Platonic realm. And it's not clear to me that the Platonic realm is dependent on the physical or vice versa. It seems like they're distinct. So at least there would be a dualism. It seems like we can make this triality, this triangle, into a rectangle because the physical itself splits into quantum and classical.
Okay. I'm not sure, you see, how distinct they are, all that. It's a useful... Yeah, okay. When you say quantum mechanics, you see, I'm not saying that's a separate world, because it's all the same world. But these are notions of reality, which I find useful to think. I'm not sure whether I tie that in with the philosophy so much. I think it's both physics. They're both physics, you see. The quantum reality and the classical reality. Whether they are even separate, or whether they're maybe you have some continuum spread between the two and so on. It's just a useful way of
thinking about quantum theory's relationship to classical mechanics, or the measurement
more
problem.
Thinking about I'm saying it's probably a temporary position to hold. Probably. See, I worry about that a bit. I mean, it's just say quantum reality and classical. Maybe there's a whole different, maybe a continuum of possibility. I'm not wanting to. I'm not trying to be dogmatic about that. I just think it's a useful way to think about certain things. See, particularly, one thing I wished I'd put in, you see, the article which I discuss these ideas most completely is in a book edited by Shan Gao on consciousness and quantum mechanics or something. It's just a collection of articles, and I have an article in that book. I think it's Oxford University Press. And I have an article in that book where I describe this quantum reality and classical reality. But one thing I rather regretted is not putting in something which I could have done, because I have a nice picture of it, which is with EPR, Einstein-Podolsky-Rosen situation. You know what I mean by that?
Uh-huh.
So you see Alice and Bob are presented. There's a spin zero particle. It splits into two spin halves. Alice and Bob each have a sealed box where they're not allowed to see this. And they go a long way off, light years away, maybe. Certain point, Alice opens her box, and okay, it's a spin half particle, so she has to choose a direction and say, okay, are you spinning this way, yes or no? And it says, nope, you got me wrong. It's the other way. So it fixes her spin as the opposite. Now, Bob's must therefore be the opposite of Alice's. But when? Well, you see, people worry about this, and John Bell used to argue about these things, all that. But my view, to make it relativistically invariant, you have to go along the past light cone. So you go along the past light cone backwards in time to earlier time, if you like. And that his particle is now flipped to be the opposite of what Alice measures. Now that's sort of retrocausal. Now, isn't that going to land you in all sorts of paradoxes? No, because it's quantum reality. If Bob could say, hello, particle, which way are you spinning? Yeah, you'd be in trouble. But all Bob can do is decide on a direction and then say, hello, particle, do you happen to be spinning this way or the other way? Says, you got me right this time. Doesn't tell him that it's a spin. He can't. The very fact that it's quantum reality means he can't ascertain what the spin state is. He can only confirm it. If he has reason to believe that it might be so-and-so, he can test that whether that's right or not. This is the Einstein criterion. But the Einstein criterion is only quantum reality. It doesn't tell you, you can't ask the system, hello system, what's your state? It looks blankly at you and says, don't ask questions like that. Suggest a direction. And you need that point of view to make sense of it. And I like to put the whole picture, you see, of Alice and Bob and the different regions where the state is so-and-so. And it's all consistent over the whole picture. I find that quite surprising. That the actual quantum reality of all over the whole picture is completely consistent. I'm slightly regretting not having put this picture into my article. But maybe that'll be a new article. I think I should. You see, I'm supposed to write up my Basil Hiley lecture, and I was just reminded. Somebody said, "Oh, look, when are you going to produce your article which on this?" And I said, "What? Oh, I'm supposed to do that?" And he said, "Well, I'll give you a little bit more time, thanks." So I have to write this article, and maybe I can put this in. You see, I think I mentioned it in the actual lecture, showing Alice and Bob and all that stuff. And you can have a nice picture showing what the quantum reality is all over the whole picture. And it's completely consistent. But it has a quite funny kind of causality relationship. It's not the ordinary way of propagating within the light cone. It's sort of without the past light cone, which is very strange.
Now, I'd like to end on how you view the state of current theoretical physics, fundamental physics. When I ask this to people, they tend to split into two camps. One that says there are some problems, and then they split into some camps as to what the cause of that problem is. Maybe they'll say, Well, the cause is that experiments are just too expensive to run to probe even deeper than we need. The problem is that quantum mechanics is too successful, and it would be great if there was something that was disagreeing with the standard model.
It's funny how people see how successful. Well, you see, there are all tons of experiments where you don't perturb them. It's way below the Dioschi level, you see. So these experiments, and it works extraordinarily well. Sure it does. But you don't move much mass. There's a huge story there. So if you're asking me, am I one of these people we're nearly there, just funny details, I'm not one of those people. I'm one of the people that said, no, there's a big theory behind that we just don't know at all. If that's what you want to know.
I want to know if you've noticed a difference over the past few decades as to how fundamental physics is researched. So, for instance, as I was mentioning, there are two camps, one that thinks it's gone awry for some reason, and one that thinks, no, it's broadly on track, and it's operating as usual. We're just dealing with extremely difficult problems. What do you see?
I mean, it's probably the same as the quantum issue, if you like. Because it works so well when you don't move much mass around, people get sort of convinced that it's the full answer. And I don't think that's right at all. No, there's a huge thing missing.
Is that why in our first conversation, you mentioned quantum mechanics is wrong or quantum theory is wrong? And then, of course, the objection is, well, it's extremely accurate. You could say it's incomplete. That's not the same as it being wrong. So is that what you mean? That, look, sure, quantum mechanics is extremely correct.
I like to be ruder about it, you see. See, Schrödinger and Einstein were much more polite. They said, well, quantum mechanics is incomplete. Okay, you can say that. I like to be more brutal and say it's actually wrong. But I mean, that's fine. We're not really disagreeing. It's just terminology. I'm saying that it's a big thing that's missing. Incomplete rather suggests, oh, there's a little detail. Oh, change the sign here. Oh, that's it. I don't mean that. I mean that the broad framework needs overhauling. And in the limit of not much mass displacement, it's quantum mechanics. Sure. If you have mass displacements, it goes wrong very rapidly. You know, so people say, well, about what the Planck scale, you see, well, what is the Planck mass? The Planck mass is a flea's eye, more or less.
Yes.
If you put a flea's eye in two places at once, maybe with the fleas looking that way at the same time, does it collapse the wave function? Yes, because a flea's eye is a Planck mass, and it collapses in a Planck time. What is the Planck time? 10 to the minus 30 seconds or something. Ridiculously small time. So it would be flea's eye is classical because the collapse time is so tiny. In experiments, sure, I'm not an expert on experiments, but the experiments which have been done, which show you quantum mechanics is right, there's practically no mass displacement involved in these experiments. So of course you get the right answer. I mean, of course. It's amazing. I'm not saying of course, really. Quantum mechanics is an amazing revolution. There's no question about that. I do agree with that. But if you're considering displacing masses, it gives you the wrong answer. In a tiny fraction of a second. It's saying that because certain things work so well, tells you the theory is right. No, it doesn't. Because all these experiments are in a regime where you hardly move a mass around at all.
Is there any piece of advice that you consistently give your students?
No, because I don't have any students.
Or
anyway, I only taught mathematics, you see. I was always in I'm in mathematics departments. I taught mathematics. I did teach quantum mechanics, that's true. And I would waste a lot of time. I realized what a fool I was. The whole first 2 lectures I wasted because I was all on this stuff, the philosophy of it and why wave function collapses or something. And I shouldn't have been wasting my time on that because I had to race at a great speed to try and catch up with the syllabus.
Mm-hmm.
If you want to teach the course, you have to teach what's in the course, not trying to explain why the thing. But then people obviously worry about it, and there is this feeling somehow that big systems, because you it's too much trouble to make the quantum state of a big system, or else you're like the philosophers used to be in Oxford. I don't think they're like that now, where you go into the many worlds picture and say all these different alternatives coexist somehow. And the reality of the situation is a huge mass of all the different things that might happen. And somehow a conscious being threads its way through this huge entangled mass of things. So that's one resolution, if you call it a resolution, which used to be keen on the philosophers. And I'm not sure whether it's true anymore, because the person... There's a funny story there. David Wallace, I think that's his name, yes. But he's gone to Princeton. I remember going to a very small conference, about 6 people, and we were discussing these issues. And David Wallace is one of the people. And then the thing all finished, and I thought, well, I'm glad this is all over. And then I'd go home, and David Wallace said, well, is it all right if I walk with you? I said, yeah, that's all right. So I chat with him for a while. And I hope when we'll get to a corner where he goes off and we go a different way and I can relax a bit. No, he turns the same way. No, this way. No, he turns the same way this way. Oh well, we're going to the same flat complex. Comes in the same door as me. Go up, same floor. He's just down the corridor from me. He doesn't live there anymore now because he's gone to Pittsburgh. That was funny. The chances against that must be quite large.
Have you ever spoken to Douglas Hofstadter about your theory of consciousness and Gödel's theorem?
Okay, I'll tell you my Hofstadter story. I was going to have lunch with him, which I did. But before lunch, there was an occasion where we could discuss things with him. And I read his book, and I knew his point of view, and I thought he'd come to the wrong conclusion. And I had decided I was going to paint him into a corner. You see, so I started painting him into this corner. And the corner I was going to paint him into is that certain integers are conscious.
Right.
And I only got, hardly got into the corner. He simply leapt into the corner. What, you mean to a certain integer conscious? Yes. That was my Hofstadter story. I think we had quite a nice lunch afterwards, but I just find it so extraordinary. I mean, quite consistent, because that was the view that he was driving for. But it seemed to me an absurdity. But he didn't think it was an absurdity. He just thought, some integers happen to be conscious, that's all. Okay, well, you can think that if you like.
Professor, I've had such a great time speaking with you.
Okay.
Thank you for spending 2 hours with me.
Oh, goodness. I hope I'm not wasting the time. Yvette should have been here.
Yes. Yvette just came through the door. And just for the people who are wondering what this is about, Yvette Fuentes is now coming, and we're going to do another podcast jointly on Yvette Fuentes.
She's by herself first. Is that right?
No, she's going to be with you, but we're going to take a break. So there's 3 podcasts. There's this one with Roger solo. There's one with Yvette and Roger. And then there's one with Yvette solo.
That's what I was expecting.
Yes.
Yeah. Oh, she's doing an experiment, which is testing this idea about the state reduction, which is a very important experiment, as far as I'm concerned.
We're going to talk all about quantum gravity and collapse models with Yvette in a few minutes. Okay. Thank you.
No, it's always been great fun. Thank you. Yes.
I hope you enjoyed that interview with Sir Roger Penrose. There's another interview with said Sir Roger Penrose coming up in a couple weeks. In that interview, we discussed a sensitive experiment. It's in the pre-publishing phases currently, that experiment, or at least the results of it. And so once it's officially published, then I have the go-ahead to launch it, so subscribe for that. Now, it takes a huge amount of time to prepare for interviews like this. I study the guests' papers, I study adjacent fields, I construct quizzes for myself, and then perform those or test myself for weeks prior. I then also talk to the guests' colleagues often so that I ensure that I have the guest's point of view correct in my head and that I'm not wasting the guest's time or your time. It also takes a considerable amount of money to travel from a place like, say, Toronto to Oxford to film with Roger, or to film at Boston, at MIT, or Harvard. People think that YouTube ad revenue is high. However, in science and philosophy, they're one of the lowest paying categories. So I directly rely on the support from generous donors, such as potentially yourself. If you have the funds and you're willing, then there are 3 primary ways to contribute. One is to become a founding member on Substack. Of course, becoming any paying member on Substack is great, but the founding member is the top tier. Number 2 is giving a one-time donation via PayPal. And number 3 is to give a one-time donation via crypto. Links to all of these are in the description. Many people think that Theories of Everything, this channel is a huge team, it's a huge production. Actually, it's just 2 or 3 people. It's myself and my wife, and of course, the full-time editor who is editing this. Thank you. And that's all to say that your donations go a long way. Thank you for getting us over 500,000 YouTube subscribers. That's magnificent, and it's all thanks to you. Thank you.